就掌声欢迎本身业务带来的
Thank you. So what I would like to do is provide you some examples of how MATLAB and Simulink can be used to developing algorithms for robotics and autonomous systems. As I said in the morning, the intent for today is to give you some ideas about how you can develop some of these new autonomous systems using the capabilities of MATLAB and Simulink. So when you think about smart systems, you hear about drones like this. This is the Amazon drone that is supposed to someday deliver packages automatically to your home so that there is no need for a human being to deliver those packages. Also, okay, give me just 1 minute. Okay, so this is the example that Georgia showed in her talk, and I'll talk a little bit more about this example as well today. So these are all good examples, and what I would like you to leave today from this talk is these are the key takeaways, which is if you want to develop some of these smart autonomous systems, then your success and how effectively you can develop these autonomous systems will come down to these 3 factors. One, inherently these robotics and autonomous systems are what are called as multi-domain. What I mean by multi-domain involves a combination of things like electricals, mechanicals, software, controls. And in order for you to develop these sophisticated, complicated systems, it is really, really important that you do a complete multi-domain system-level optimization of your design. And that is only possible when you do multi-domain simulation. The other part that I would like to emphasize is that earlier this morning, I showed that complete workflow about accessing data, processing the data, and then developing the models and deploying those models. In developing these autonomous systems, you have to span that complete workflow. Only then can you successfully design these systems. And the third key takeaway is that model-based design is very well suited. Model-based design with MATLAB and Simulink can help you develop these systems. So I'll show you some examples of how other engineers and scientists like yourself have done this, and hopefully that will spark some ideas and some discussions in terms of how you can do this too. In terms of when you're developing these kinds of systems, when we talk to customers of ours who are working on developing these systems, these are some of the challenges that they tell us. We already talked about the need for end-to-end workflows. The other aspect that is really important is the complexity. These systems are inherently complicated. And this is what stresses the design and development process significantly. So we'll look at how some of these challenges can be tackled in the course of developing these systems. So what does success look like when you completely develop this system? What would it look like if you're successful? So here's the example from DLR. This is just one. As you can see, it's almost like a human being. You can lift, and then you can see it do some sophisticated assembly tasks. In this case, it can do some image recognition, video recognition. It can identify the ball, where it's going, and then reach the hand so that it can grab the ball. It can also throw the ball, not just grab it. As you can see, there is significant complexity that goes into designing these kinds of systems. So how do you get started, what do you do, and how do you go about building these systems? So to keep it manageable, we break it down into some key components. The first part is what we call as platform. What do I mean by platform? So in the case of Justin, this is the robot. The platform includes things like the mechanical hardware, right? The motors, the shell of the robot, right? The joints. All of these things are what we would call the platform. Now, platform by itself cannot do much. You need to add sensors. In the case of Justin, there are multiple sensors. There are sensors, as you saw, he can look at the human being that's throwing the ball. So there's a camera sensor that can then take that information in. There are sensors because it wants to move its arm to either throw the ball or to catch the ball. There are sensors in the different joints. So these are all examples of sensors. Then, once you have all this sensor information, you need to proceed. So just because you have a camera, that by itself doesn't do anything, right? The camera, you need to get the information to the camera and identify where the ball is, right? And more importantly, not only where the ball is now, but where the ball will be 5 seconds from now, so that you can make your arm go there and catch it, right? So that is what I mean by perception. Then you have to plan and decide. So when you know that the ball is going to be here, then you have to plan how the robot is going to move its arm to go there to catch the ball. So that is what is called as planning and deciding. There might be some obstacles in the way. Maybe the robot arm cannot go there directly. Maybe there are some obstacles it has to go around. All of that is part of the planning and deciding. And then, once you plan and decide, you have to make sure that the real robot actually does follow your plan, which is the control aspect of it. So anytime you're designing and developing an autonomous system, these are the key things that you need to worry about. Platform, sensing, perception, planning and deciding, and controls. And whatever tools or techniques that you will use, they need to span these complete spectrum. Otherwise, what will happen is if you get a tool that's only good at this, but not at the other elements, it will be very hard for you to develop an overall optimized system. So, in this case, we looked at robot, but it's not just about manipulator arms or robots that look like human beings. You can think of a car as a robot, right? Because today you have self-driving cars. You can think of that as a robot too. It just happens to have different kinds of sensors. Earlier this morning we saw the LiDAR sensor, which is the LiDAR, the radar, the camera, and so on and so forth. The platform in this case is the car itself, the mechanics and the dynamics of the car. And then the control, there's an array of different things you can control on the car. The steering, the braking, the acceleration, and all those things. And what makes all of this work from when you get to an automated driver car is all the other stuff that goes around it, which is you need to know where the car is, right? You need to know what's around the car so that you can safely navigate the car. So that is what we mean by all these different things: obstacle avoidance, localization, and as well as you might do something called as platooning, where your car might be following the car in front of it. All of those things can be done. And then this is where we talked about deep learning and how it can make that problem easier to solve. So take a look. Let's start with taking a look at how you can do a pick and place application. So for the first thing, what we'll do is, this is an example of MATLAB and Simulink model that is running. You see a couple of things going on here. It is identifying these chocolates, the candy bars, in this case it's Snickers, and then it is telling the robot to go pick that candy bar. So how does it do that? So there is an array of different things involved. Here you see state flow being used to control the robot, because anytime you are doing a task like this, there are multiple different states involved. The robot might be in a standing state, then you want to move it to a different state. So all of that logic can be modeled using state flow. Then you want to have some visualization of how the robot arm itself behaves. So all of this is simulated using a MATLAB and Simulink model. And only after you do the simulation, then you can deploy it onto the real robot and make sure it works on the real robot as well. So in order to design something like that, where do we start? So the first place we can start is on the platform. In this case, it's the robot arm. So how do I go about building a model of the robot arm? What help is available to me to get started? So a typical platform has these components. There's the mechanics, so you take the arm, there is the metal that goes in, there is the motors, which is the actuator, and there is the environment, which is what the robot arm is interacting with. So first things first, for the mechanical part of it, if you happen to have a CAD model of your robot, then you can automatically import it. In this case, what this is showing is that there is a CAD tool called SolidWorks. From SolidWorks, you can export that into what we call as SimScape multibody, and that allows you to automatically create that model inside our Simulink. Okay. So this is a very powerful tool and capability that's available to you. Instead of building the model from scratch, you can start with your CAD model and automatically export that into a SimScape multi-body model. Significantly speeds up the process of developing these models. So that is just one way. It also works with some other CAD tools like Pro-E and others. In the world of robotics, there is a standard called URDF. I forget what the exact acronym is. I think it's Unified Robot Description Format or something like that. So if you happen to use URDF, it's actually even more simple. If you have a URDF file, you can use this command in MATLAB called SMI import, and it will create that SimScape multi-body model for you. So these are some of the investments that the MathWorks has made to make it easier for you to get started to create the model. Once you have the model, then you need to do things like forward dynamics, inverse dynamics, calculate how much effort, how much torque it takes to move the robot. So all of that can be simulated using Simulink and all the other add-on tools that we have. If you want to cover multiple domains, I've worked with customers who work, for example, with pneumatic robots or hydraulic robots. So in that case, you would use something called as SimScape fluids to model those kinds of robots, as well as there is all kinds of different drive lines. If you happen to have gears and things like that, there's a bunch of different gear types in the driveline block, as well as in the electrical area, we have a couple of different building blocks that we can get started with. The other aspect that becomes important here is that there are existing robot simulators out there that other companies have built. So this example here is a robot simulator out there called Gazebo. So from MATLAB and Simulink, you can interface with Gazebo. So you can have your dynamics model inside of MATLAB and Simulink. You can interface it to Gazebo to do the visualization of how the robot works. So here, what you'll see is this is the MATLAB Simulink model of the controller, and then the visualization gets done in Gazebo. And the beauty of this is that you can debug your overall system using this connection between MATLAB Simulink and Gazebo. You can see how the system behaves in the real world. You can make some changes to your control algorithm, for example, see how the performance of the robot changes when you make those changes to the controller parameters. You might have some PID gains and things like that. All of those things you can interact, you can do a interactively tune and optimize your overall system. Once again here, you see the state flow chart. It can tell you which state the controller is operating right now. And this significantly enhances your ability to debug the system and make sure that there are no errors in the system. Okay? In addition to that, in the world of robotics, there is something called as the ROS, Robot Operating System. So from MATLAB and Simulink, you can connect to ROS in many different ways. One easy way to connect is that if you have a Simulink model, you can generate code from it and turn that into a ROS node. From MATLAB itself, you can talk to other ROS nodes. If you have ROS data, you can import that ROS data into MATLAB for analysis, as well as using ROS, you can connect either the physical robot, which can be a manipulator or a ground robot, or you can connect to the simulation environment, like the Gazebo that we saw earlier, or you can establish a ROS node that's controlling the robot. So these are many different ways in which you can control MATLAB, you can connect MATLAB and Simulink to ROS. Okay. Now let's move to the sensing part. So there's a array of different sensors. The examples that you saw, that video that you saw earlier, was using the Connect sensor. And with the Connect sensor, you can do sophisticated analysis with it. You can do things like image analysis. You can do point clouds. So in the talk this morning, I showed you that auto live example, which had the point cloud data from the car that was moving around, moving on the road. So all of those point clouds can be processed. Abhijit showed you in the What's New in MATLAB Simulink how we can tag data, tag those point clouds with information. We can do some semantic segmentation to identify the background from the other areas of interest. So all of those things can be done to improve your ability to sense what is going on in the environment. As I said before, once you do the sensing, then you can get to the perception. In the case of the candy bar example, you need to estimate the pose, right, as to whether the object, for example, how the object is oriented. All of those analysis can be very easily done, and you can identify those objects irrespective of the orientation of those objects. This is something we talked about earlier, which is using machine learning to do some of the object recognition. And not only machine learning, but also deep learning in the cases where it might be more challenging for you to identify the features. So when you have all these capabilities, you can bring them together using MATLAB and Simulink and use that to develop a end-to-end learning environment that allows you to identify the features as well as classify the features. Okay? So here's some examples of how MATLAB can make that easy. So this is what you see here is actual MATLAB code. So it doesn't take that much code to turn these images into information that you can act on. Right? In this case, this is 5 lines of MATLAB code to get to the area of interest based on the image feed that is coming in. And then, as I said before, we can apply the classification learner app to classify these things. And this is in the video that shows you, in this case, it is recognizing that this is a Snickers bar, this is a Reese's bar, this is an M&M, and this is some other kind of candy. It's also doing some sizing. So it's, for example, recognizing how big the objects are, right? So all these kinds of algorithms are developed, can be developed using MATLAB Simulink. Then you can deploy these out into the real world. The next step here is the planning and deciding. So this is where you would do things like motion planning. So earlier I mentioned that one of the most common challenges when you're working with a robotic system is to help the robot maneuver around obstacles. So that is where we talk about developing a plan or path. This is the robot, it needs to move from here to here. These are some obstacles along the way, and you need to plan your path through those obstacles. There are a variety of different approaches you can take. Some of our customers use state flow to do this planning. One of the nice things about state flow is you can take a very nice hierarchical modular approach to developing your planning algorithms. So you can break it down into the different steps involved. You can do some joint control to move the robot. In this case, there's a gripper. So you have a separate state chart for the gripper control. There is inverse kinematics control. So for those of you that don't know, inverse kinematics, basically if I know that I need to go to that point and it has some XYZ coordinates, how do I tell the robot joints to move to get to that XYZ point? So all inverse kinematics is, it maps those XYZ Cartesian coordinates into the joint coordinates of the robot. So then you can command the robot to go to those joint coordinates and thereby reach the Cartesian coordinate that you wanted to get to. And it's not just about getting the endpoint, but getting it around the obstacles. That's where you can do waypoint control using the state flow chart. Okay. And in terms of how do we make things like inverse kinematics easy, there certainly are a number of different built-in functions. Georgia this morning talked about some of the new features in 18B, and this is one of the things that she mentioned, that there are some built-in functions, for example, to do inverse kinematics in the robotics system toolbox. And once again, this is how it all comes together, and it becomes this environment that allows you to develop, debug, and tune your robotic system across different domains. Earlier I talked about how you need to transcend electrical, mechanical, controls, software. So Simulink becomes that environment that allows you to transcend all those domains, bring it all together in one unified environment. So as I said before, the key takeaways from this talk are you need to have a multi-domain simulation environment. MATLAB Simulink provides that. You need to have tools that span the complete workflow. MATLAB Simulink allows you to do that, as well as the model-based design approach. So what I want to do is take some time to show you some examples of how other companies are doing this today. Okay? So first example is the Justin robot. You saw that video earlier. In this case, this is the work is done by DLR, which is a research center in Germany. And just to give you an idea about the complexity of the robot, in this case, Justin has 53 degrees of freedom, right? So basically, there are 53 motors and actuators that are moving that need to be optimally told how to function. So what DLR did is that they used MATLAB and Simulink to model the physical robot itself, Justin, as well as to model the controller, just like I said before, so that you can simulate the entire system. Once they did that in simulation, then when they went to the real-time implementation, they did not have to write the code by hand. They could automatically generate the C code from those Simulink models. And those C codes were used in a couple of different ways. You'll see this thing here called HIL testing. All HIL testing is all about is hardware-in-the-loop testing, where how do you do testing when the real robot is not built yet? So instead of waiting for the real robot to be built, what you do is use a simulation model of the robot, run that on a real-time PC, and then connect your controller to it. The controller thinks it's controlling the real robot, but instead it's controlling the real-time simulation of the robot. And by doing that, you can get a complete verification of how your system performs. So in terms of some of the benefits that they saw, certainly programming defects eliminated. That's because the software was automatically generated. As Dr. Baumel says, code generation using Simulink Coder eliminated programming defects. But more importantly, they used to have all kinds of functional defects before, and they were reduced by about 80%, which is a significant improvement over what they were doing before with hand coding. The other key benefit is the time, which is, so in that video you saw the throwing motion. Justin was either throwing the ball or catching the ball. And in this case, for that throwing motion, Justin, in this case, is controlling 20 different degrees of freedom. So you can imagine the complexity. It looks like a very simple motion, but you're controlling 20 different motors and actuators and telling them how to work. All of that work in terms of doing the trajectory planning and the control, they did that work in one afternoon using MATLAB Simulink and optimization tools. So that is the significant power you have in terms at your disposal when you're working on systems like this. That is how you design and develop these complicated systems in the short amount of time that's available. And it's not just about robot manipulators, it also works with ground vehicles. In this case, this example is from Clearpath Robotics. They made this auto self-driving vehicle. In their case, they are using different kinds of data. So they use a LiDAR scanner, laser-based perception, and also they want to make sure that the robot can navigate and move on its own. They are using the robot operating system in this case, and because of MATLAB's connectivity to ROS, they can bring in data using from the ROS bags into MATLAB, speeds up their data analysis time, as well as allows them to develop some very sophisticated algorithms that allow that robot to navigate on its own. This one here, it's a company called Voyage that developed these self-driving taxis. So this is an example of automated driving. So in this case, you can think of the car as a robot. And what Voyage does is their market is very narrowly targeted. So they are focused on what's called as a retirement community. So these are villages or small parts of the town where people who are no longer working, they have retired from work, they live, and one of the things that they're looking for access to is a very quick and easy way to get from point A to point B. One of the very powerful examples from Voyage is somebody who's blind, and because they're blind, they cannot drive, it's very hard for them to go from point A to point B. But by using this self-driving taxi, they can get to wherever they want. So all of that work was done using MATLAB and Simulink. They used MATLAB and Simulink to design this model-predicted controller. Model-predicted control is a, let's call it a class of optimization techniques that is very useful in these kinds of applications. So they developed a controller and then they deployed the controller as a ROS node using the robotic system toolbox. Certainly, they were able to do this significantly faster, as well as they were able to integrate with ROS, which is open source, and then the source code was generated in MATLAB coder into a Docker container. Docker containers makes it very modular for you to design and develop these systems. And the thing I really liked about this example is that they had a very small team. It's not like they had an army of 100 or 1,000 engineers. So as you can see here, their team of 3 engineers completed the initial braking and acceleration control system for the self-driving taxi in just 2 months. So that is one thing I really want to make sure you take away from this, which is these kinds of systems are not limited to large companies who have hundreds and thousands of engineers at their disposal. Voyage is a startup, so they had a very small team of engineers. And the reason they were able to get this done in a short amount of time and very quickly is because they use MATLAB Simulink as part of their work. And this one is about bipedal robots. So basically, in this case, it has 2 legs. The dynamics and the control problems are significantly more challenging in this case because, as you may or may not know, anytime you're standing up, you're unstable. Your body is not designed to be stable. Your muscles are doing a lot of complicated actions to keep you standing vertically. So that by itself is a fundamental challenge. In this case, this is a startup that came out of the University of Michigan. And again, very small teams, many of them students working on developing these complicated systems. They were able to get this done very quickly and get this robot out there as part of their startup that they formed. And then this is a company called Festo. This is what's called as a bionic arm, and this is used in an industrial setting. And because of the industrial setting, in this case, they are using PLCs to control this arm. It has pneumatics built into it, and the pneumatics controlled by PLC. And in the other examples that we saw, MATLAB and Simulink was being used to generate C code. In this case, the difference is that MATLAB and Simulink is being used to generate PLC code. So as your needs change, sometimes you might want to generate C code, sometimes you want to generate PLC code, or GPU, or DSP. That's the beauty of it. You can keep your IP in the MATLAB Simulink model, and as your needs change, you can generate code appropriately. The same benefits that we saw before, we were able to get this done faster, cheaper, better. This example, this is a company called Precise. It's a startup based in Netherlands. And what they do is make robotic surgery equipment. So instead of the human surgeon operating on you, this is a robot that is doing the surgery on you. In this case, the surgery is being done on your eye. So it has to be very, very precise. So hence the name of the company, which is Precise, which is like a double meaning thing, precise both in terms of surgery and the fact that it's operating on the eyes. So they are a startup, as I said before, right? So one of the key things here was the founder of this company. He was a one-man army, and he was able to develop this complete system, including the modeling and simulation, and then doing the real-time deployment onto the robot using Simulink real-time. And these are some of the key benefits. As I said, one engineer worked on the whole thing. They had really strict requirements on the patient safety. As you might imagine, you don't want anything to go wrong. So all those safety critical type situations were handled through some of the smart logic inside the Simulink model. And this slide itself is about a year or so old now. We are beyond this startup phase, and now they're selling this equipment to hospitals and other companies. So hopefully that gave you a view of how MATLAB and Simulink can be used to develop smart robotics and autonomous systems. We have many of these examples outside in the exhibit area. So what I would request you is stop by and see for yourself how these things work. And that will give you hopefully some ideas about how you can apply these techniques in the context of your work. Thank you.